Here I'm going to give an example of how one might use the technique of unfolding to evaluate an inner product. So here we're going to take f to be a weight k holomorphic modular form. With character chi. And we're going to consider the inner product of y to the k times the absolute value of f squared against our Eisenstein series. And here our Eisenstein series is going to be without a character because we're taking the absolute value squared. So this is a common trick that y to the k times absolute value squared of f, where f is like this, is weight 0 trivial character. And you can verify this directly just by applying, just by using the definition of how this transforms. So let's write out our inner product. So this is the integral over gamma naught n modding out the upper half plane of y to the k times f of z times f of z bar times, and here I'm going to write sum gamma in gamma infinity modding out gamma naught n. We have no character, and this is the imaginary part of gamma z. And now here I'm gonna use some trick. It's actually much more convenient notationally to take the inner product with s bar. It's the same later on, of course, and you're just a change of variables here, but it means that you don't have to carry around s bars. So I'm gonna look at this. So here, this is the imaginary part of gamma z to the s bar, and then I'm gonna write my asterisk to mean complex conjugation. And then we have our usual measure. And the using the unfolding trick, this is a shortcut that you can take. You can just say that this is going to be, with the reasoning from the first lecture on unfolding, this is going to be the integral over the upper half plane mod gamma infinity, the stabilizer, of y to the k times absolute, times f of z times f of z bar times, and now we have conjugate, so this is just y to the s dx dy over y squared. And writing out this quotient explicitly, this is the integral. Y is going from 0 to infinity, and x is going from 0 to 1. And here we have f of z, f of z bar, and that's the only x dependence we have. And then we have a y to the s plus k minus 1 dy over y. Okay. Now this step to compute this integral, so we're asking for the constant term of this inner product. The way to do this is to write these out as Fourier expansions. We're going to assume that these are cusp forms, so these are the sum n from 1 to infinity of an e to the 2 pi I n z, and then So this is going to be f of z essentially by definition. And then the other term is going to be some, I've got to use a different letter here. I don't have to, but it's much more convenient to use a different letter. M from 1 to infinity, am, e to the 2 pi I mz, and then complex conjugate. So this whole term is f of z bar. And we can just cross multiply. What we end up getting is a sum over m and n, both going from 1 to infinity, of an am bar, because we're conjugating the am here. And then we have an e to the 2 pi I n x from the z, writing that as x plus iy. And then we have an e to the minus 2 pi ny. So this is coming from the fact that e to the 2 pi I n x plus iy is equal to e to the 2 pi I n x times e to the 2 pi I n times iy, and the two i's here give you this minus sign. So these two things are just this term, and then for the second term, well, when we take the complex conjugate of e to the 2 pi I m x plus iy, we get e to the, you have to take the complex conjugate of the this constant, and then we also have to take the complex conjugate of the z that's appearing here. And so this is going to give, this complex conjugate is going to turn this I into a minus I. So you get e to the minus 2 pi I mx times e to the minus 2 pi my. So here we get e to the minus 2 pi I mx, e to the minus 2 pi my. So this is what this product is equal to. And now we're going to be integrating from 0 to 1. So to figure out what that's going to be, let's rewrite this just for emphasis. This is sum mn going from 1 to infinity of an times am bar. And then here I'm going to write e to the 2 pi I n minus m x, e to the minus 2 pi n plus m y. So for integrating this series from minus 1 to 1, and so our inner product is the integral 0 to infinity, 0 to 1 of the sum mn from 1 to infinity of m bar. And now I'm going to swap the order of these two things, e to the minus 2 pi n plus m y, e to the 2 pi I n minus m x dx, and then we had a y to the s plus k minus 1 dy over y. So for this integral from 0 to 1 to be non-zero, we're going to need m is equal to n, because if these are different, the only x dependence that appears in this integrand is in this term here. And for that, I mean, if m minus n is not it's not 0, then you're just integrating e to the 2 pi integer x x going from 0 to 1. That gives you 0. So what we can say is that this integral is equal to the integral y going from 0 to infinity of the sum n from 1 to infinity. Here we have the absolute value squared of an, right, because n has to be equal to m. And then we have an e to the minus, so again, n has to be equal to m, so this is minus 4 pi ny, y to the s plus k minus 1 dy over y. Here the way forward is to swap the order of integration and summation. So it gives you the sum n from 1 to infinity of absolute value squared of an times this integral 0 to infinity e to the minus 4 pi n y to the s plus k minus 1 dy over y. And now for each of these, for each term in the sum, we're going to make a change of variables. We're going to make the change of variables y. We want this this thing in the exponent to be just y. So maybe the way to write this is going to set u to be equal to 4 pi ny, which means that du is we don't have to worry about the du because this is the Haar measure for the reals under multiplication. So it's going to be invariant under just scaling our y. So what we end up getting is the sum n from 1 to infinity of an squared times the integral 0 to infinity e to the minus u, and then the y here is u over 4 pi n. And then we have s plus k minus 1 as the exponent, and then we have du over u. And if you're unconvinced that this is invariant, of course, you can just work it out very easily. Now here this 4 pi n has no u dependence, so we can factor it out. Sum n from 1 to infinity of an squared over, here we have 4 pi n to the s plus k minus 1. It's the same for each piece. And then we have this integral from 0 to infinity of e to the minus u to the s plus k minus 1 du over u. And now this piece, in general, you go and you look up whatever Mellin transform you get in a table of integrals, but this one we can just recognize directly as being a gamma function. This is gamma function evaluated at s plus k minus 1. Right, because recall that gamma of s is defined to be the integral from 0 to infinity of e to the minus t to the s dt over t. So what we end up getting as the value of our inner product is gamma of s plus k minus 1, and then here we can bring out the power of 4 pi that appears. So this is 4 pi to the s plus k minus 1. And then what we're left with is the sum n from 1 to infinity over of an absolute value squared over n to the s plus k minus 1, which is the value of some L function. So if you want, you can write this as integral s plus k minus 1 over 4 pi s plus k minus 1 times the L function evaluated at s plus k minus 1, and then here I'm just going to write f squared to, just to mean that we're taking these Fourier coefficients. And this notation is not what people usually use, but it's just to emphasize that this is the value of some L function in this case. So using the technique of unfolding, what we found is that our initial inner product was equal to this. So we're saying that the inner product of y to the k absolute value of f squared with our Eisenstein series evaluated at s bar is equal to the gamma function s plus k minus 1 over 4 pi to the s plus k minus 1. And then here I'm just going to write the series definition because it's standard notation. Cool. So that's an example of how you would use the technique of unfolding to evaluate an inner product like this.